In subtopic 11.2, power generation and transmission, we're going to look at how electricity is generated. In order to do that, though, we need to refer back to 11.1 on electromagnetic induction. So just to briefly tie back into that subtopic, the idea that we're going to look at is generating an EMF. And if you recall, in order to generate an EMF, a conductor is moved through a magnetic field. So that's the basics of any form of electromagnetic induction, so a conductor moving through a magnetic field. If we then look at a generator, basically a generator is, or an electrical generator, let's be a little bit more specific. An electrical generator is basically just providing a way in which that conductor can continually be moved through a magnetic field. And so as a result, an electrical generator converts kinetic energy of the conductor into electrical energy. Now, in order to make sense of this idea of a generator, we'll have a look at sort of the simplest way that you could construct a generator. So we'll start off with a diagram representing how that would be done. We will elaborate a bit more on this in class and look at a few different scenarios, a few different aspects of this type of generator. It basically consists of north and south pole to set up a magnetic field. Now that could be a horseshoe magnet, or it could be two separate magnets. Exactly how that magnetic field is established isn't particularly important. So basically we just need to have a magnetic field positioned, or magnetic field in this particular region, and around that region we're going to have there's going to be a conductor, and we're just going to represent that as a simple loop. So here's the loop that we're going to be dealing with, and we'll start off just looking at the loop like that, and we'll develop this as we go. One other thing to mention here, along sort of through the middle of that loop, we're going to have an axis of rotation. So just keep in mind that this loop is now going to be moving through that magnetic field, but it's going to be rotating, not just moving up or down, left or right. So the rotation that we're going to have here, we'll say that it's in that direction, so in a clockwise direction. To make this a little bit easier to understand, we'll refer to particular points on this loop. So X can be that part of the loop, Y will be that branch. Then the corners of the loop, we'll call that A, B, C, and D. So that's just for reference sake, so that when I'm referring to that particular generator, we can talk about what's happening in that scenario. So in this case, we're going to have that loop rotating around the axis of rotation, so that initially AB will be coming down through the loop as it rotates around this way, and then after it's rotated halfway through one full revolution, AB will then be moving back up this way. Likewise, C and D will be doing the opposite, so C and D will be moving up that way, and then coming back down the other side. So there's a very simple generator, but there are a few things that I want to talk about in terms of how electricity is generated in this case. I'll also just briefly mention here, in the next video we'll look at what actually happens down at these two ends here of X and Y, so we will come back to that later. Now, in order to make sense of how a generator works, we also need to recall from 11.1 that EMF is given by the equation negative N delta phi on delta T. More specifically, in order to explain this in more detail, we're going to look at that as being the rate of change of flux linkage, and hopefully you can recall that flux linkage is that the numerator, so basically just N delta phi. And remember that this negative at the front here deals with the direction of current flow, so it relates to Lenz's law. Now, if we look at the diagram above, if we consider that to be time t equals 0, so at t equals 0, we're going to have a look at what happens with the flux linkage, and then we'll sort of step it through as that loop rotates in that field. And in order to identify what's going on, we're going to represent it graphically. So on the vertical axis, we're going to have our flux linkage. So again, that's the n delta phi. And on the horizontal axis, we're going to have time. So at t is equal to 0, the flux linkage is at a maximum. And just go back up to that diagram. Oops. At a maximum. So if you think about that scenario, the greatest surface area of this loop is currently being presented to that magnetic field, so the largest area as that coil is rotating. So the area is at its greatest, and so the magnetic field strength, given that it's constant, means that the flux linkage will be at a maximum. So we can say then at t equals 0, we can put a mark on here to show what the flux linkage would be at that point in time. Now, after a quarter of a turn, so by looking at 1/4, we're now saying that that side AB has rotated so that it's now come down to this point here. So basically the loop, so that side BC, is now going to be parallel to the magnetic field. And it will also mean that AD would be parallel to the field, and so AB will also be in that same plane. So that now means that there is no area through which the magnetic field can pass. So if there's no area through it, then the flux through the loop at that point in time will be 0. So that means then the flux linkage will be 0. So, and that's because the area through which the field passes is 0, or the area through which the field passes is parallel to the field. So that then basically means that after a quarter of a turn, so somewhere here, so this point here would be 1/4 of the rotation, the flux linkage has decreased to 0. Now after 1/2 a rotation, that now basically means that the side AB, so basically just means that AB and CD have swapped over. If we took that initial, so when t is equal to 0 as shown in the diagram, that means that the area is the sort of the direction that we're dealing with is sort of coming from the right through AB, CD. If we've then rotated, the area is now sort of facing in the opposite direction. So basically what it means is that we've still got a maximum in terms of the size of the flux linkage, but it's now in the opposite direction. And remember that flux is a vector quantity. So after 1/2 of a turn, the flux linkage is the same magnitude as at t equals 0. But it's now the opposite direction. So that means that we now have a point over here, where we're now at 1/2 a turn, so this time here is 1/2 the rotation, has the same magnitude but the opposite direction, so it's a negative. If we then follow that through and go another 1/4 of a turn, so 3/4 of a turn, we would see that that would be here, so that would be 3/4. And if we then go one further 1/4, we're back to our original position, and so that would correspond to 1 full rotation. And if we were to then sort of step that out as we go through and do all the calculations, what we would see is that the shape of that ends up being in this case, a cos curve. And that's only because of the initial position that we started the coil. If it was initially horizontal, then it would be a sine curve. But ultimately we get this periodic function where we can see a continuing increase and decrease, so going from positive to negative in a periodic motion. So that's the flux linkage. If we want to have a look at the induced EMF, we know that induced EMF is the rate of change of flux linkage, as we said earlier. And if we're really talking about rate of change of flux linkage, what we're really saying is the gradient. We're looking now for the gradient of the graph, or the n delta phi versus t graph, keeping in mind that it's the negative as well. So sorry, just to be a pain, I should have mentioned that already. So the EMF is the negative rate of change of the flux linkage. So that now means that we can take the graph there of flux linkage and turn it into an induced EMF graph. So we're now going to have induced EMF on the vertical axis, and we'll still have time on the horizontal axis. And if we now look at what's happening in the graph up here, we can see that initially, I'll just change colours here to make it a bit clearer. So initially we've got a gradient of 0, so that means initially our induced EMF is going to be 0. If we go to 1/2 rotation, we can see again that it's 0 there, and then again at 1 full rotation the gradient's 0. So we can then come back down here and say that at 1/2 rotation and at 1 full rotation, the EMF will be 0. Now if we look at 1/4 of a rotation, that's where we're going to have the maximum slope, and so maximum EMF. Keeping in mind that here the gradient is negative, so that gradient there is a negative value, which means that the EMF at that point will actually be a positive. So we'll have an EMF then that is at its maximum, and then on the reverse of that, over here, we've got a gradient that's positive, and because we know that EMF is the negative of the rate of change, so positive gradient will give us a negative maximum, and again we'll see that it's a periodic function. In this case it will look like a sine wave that increases and decreases over time. And so there's our induced EMF for a simple generator. What we'll do in the next few videos is have a look at how we can increase or what factors affect the maximum EMF, how we can increase or decrease that, and also what's going to happen to the period depending on the rate of rotation of the coil itself.